So hello guys, this is my next video on context-free grammar. The context-free grammar, it is as the name says, it is context-free. It doesn't check about the context of your uh, sentence, like how the words are related to each other. It just care about the structure of sentence. So in these lectures, we are just caring about the syntax. We don't care about the uh, context of the sentence. So the context-free grammar, it is as in every language we have grammar. So grammar is the set of rules. Grammar is nothing but is the set of structural rules. Okay. So the set of structural rule, in case of context-free grammar, what we have, the set of rules is we define the context-free grammar as it is a mathematical concept of computer science and the linguistic. We are saying it is context-free because it doesn't care about the context. In the context-free grammar, we are having rules, we are having terminals and non-terminals. The so what is terminal and what is non-terminal? Basically, the terminals are the words what we have we are going to input. Non-terminals are once we are combining the words as we are having words can be noun, it can be verb, or it can be preposition like that. And once we combine these two, like noun and verb, this gives me a like noun phrase. So these all are my non-terminals, and terminals are the words. So like I'm having noun as talk and verb is. So these are my terminals. These two are my terminals, and these guys are my non-terminals. So, and we can have set of rules for the term. Set of rules is the non-terminals can be mm, made can be combined to give me the non-terminals. The terminals will be combined to give me the non-terminals, and we can combine the non-terminals to make the new rules. So let's take one example of this context-free grammar. Context-free grammar, mathematically, it is defined with four tuples. This is a four tuple. V you are having is a finite set of variable, or you can say it's a non-terminal symbols. X is the terminal symbols. Then R is the finite set of rules. S is the start symbol that gives me the sentence. V and X are assumed to be disjoint. So the terminal and the non-terminal sets, they are the disjoint. So if I see here, these are my set of rules. These all are my set of rules. And if I see here, this gives me, these all are the non-terminals. And the left-hand side of every rule will be having the sorry, these are my terminals. The right hand side is my terminals, and the left hand side of my rule, these are my non-terminals. These are my non-terminals, and all are my set of rules. These all are my set of rules. So I can have the rule as that may be going from non-terminal to the non-terminal or non-terminal to terminal. Both rules are possible. Why I'm saying this is lexicon? Lexicon is this is giving me all the terminals. Terminals are the words present in my dictionary. So that is what is my lexicon. So this is the definition of my context-free grammar. Uh, After defining the context-free grammar, as you checked in my previous video, in the top-down approach, we have lots of backtracking is there. If the first rule doesn't work, then you have to try for the next rule. If the first word doesn't satisfy, then we'll try for the next sentence. So, like if I'm having the 10,000 rules present in my grammar, then it has to try for all 10,001. So, lots of repetition is there. Lots of repeated work is there in the case of top-down approach. So, to reduce this repeated work, what we can have is we can apply the dynamic programming. Why repetition is avoided in the dynamic programming? In the dynamic programming, what we do is we do the memorization. There is a step called memorization. So once you do the memorization from the lookup table, memorization is nothing but is the lookup table. So you'll maintain a lookup table, and from this lookup table, when next time you require, you need not to calculate. You can directly see from the table and substitute this and reuse this. So what happened in case of dynamic programming? Once we want to make a parse tree using dynamic programming, how we do? First thing is my context free grammar should be in the Chomsky normal form, that is CNF. CNF says all my non-terminal, all my rules should be like every non-terminal can have two non-terminals, not more than two. Like we are having in the previous example, in previous video, you have seen there's a noun phrase. That noun phrase goes to determiner, noun, and the verb phrase. So here are we are having three non-terminals. So this kind of grammar, this is not in CNF form. So if such kind of things are there, then we need to convert in the form like we have to write all my rules that should be having two non-terminals in the right hand side. At most, there should be at most two non-terminal symbol in the right hand side. And there should be one single terminal in the right hand side. You cannot have a rule like if you say noun phrase goes to determiner, this kind of situation will give me an infinite loop. I cannot um, terminate anytime. So such kind of statements again not allowed. Either it is two terminal, at most there should be two non-terminals in the right hand side, but we can not even have the non-terminal goes to the non-terminal. If there is one only, then we'll be having non-terminal to the terminal. If there is one symbol, then it is non-terminal to the terminal one. And the sentence should have, there should be a rule that every sentence can be empty. The sentence can be this rule means the sentence can be empty. So, this is kind of a terminating condition. We can say we'll be defining a terminating condition because without terminating condition, my algorithm will never finish off. So, this is just a terminating condition. The sentence can be a null string. It's possible there's no word in my sentence. So, using this, first thing is whatever the grammar we are having, we have to convert. So as we learn, we need to convert my grammar in the Chomsky normal form, that is CNF form. So to convert the grammar into CNF form, what you need to do is all of the rules. First, you need to identify all the rules which are having more than two as the right, more than two non-terminal in the right hand side part. So if any of my rule that is having more than two non-terminals. So this is like this one is having more than two non-terminals. Where is my pen? So you can see here it is like there are three non-terminals here. There are one single non-terminal here. So, and the first one is okay. The first one I'm having as the uh, I'm having that is there are two non-terminals. So the first rule is okay, but the second and third rule we have a issue. So for what we need to do is we need to convert it. So what we do in case of um, when we have three variables, when we have three non-terminals, so what we do is we can add one auxiliary non-terminal, and this auxiliary non-terminal will map to the two non-terminals. And the rules where we are having non-terminal going to the non-terminal, we can substitute with the terminals. We can directly substitute the terminals. So likewise, we'll convert to the CNF form. So for converting that CNF form, you can see here in this rule, in this particular rule, we have substituted with the terminals rather than writing as non-terminal. It will be replaced with the terminals, and this one will be adding one auxiliary variable, and this auxiliary variable will be going for 2. Then again here it is non-terminal to non-terminal, so this will be replaced with the terminals. This is perfect. This rule has no issues. This perfectly in CNF form. This one is again not in CNF form, so it should be replaced with the terminals. Again, this rule has a problem, so we have to replace with the terminals. So now my grammar is in CNS form. So first thing for applying dynamic programming, first you need to convert your grammar into CNF form. Once your grammar is converted to the CNF form, this is again the rules which have been changed. Okay. So once your grammar is converted into the CNF form, what I need to do is, as I said, it is memorization. We need to do the memorization in case of dynamic programming. How we can do the memorization? We have to maintain a table. So what we have to do is we need to maintain a table. So for the table, what I need to do is here is my grammar. It is in CNF form. Using this grammar, what I'll do is I'll write my sentence in the blocks. So I have a very heavy orange book. Same I'll write in the rows as well. A very heavy orange book. In case of dynamic programming, it is a upper triangular matrix. So first we need to fill the diagonal. First thing what we do is we need to fill the diagonal. So for filling this diagonal, what we have is we are having this non-terminal A. So this is sorry, this is a terminal A. So for this terminal A, the rules that can be evoke, that is determinant only. The rule what can be evoked is the determinant only. So we'll be writing determinant here. For very, if I say see very is present in adverb only. So I'll be writing adverb here. Then we are having heavy. Heavy is present in AP and A both. Heavy is present in AP and A both. So we'll be writing AP and A both here. Orange is present in, if you see orange is present in APA and nominal, all three. So orange is present at three places. So we'll be writing all three, nominal, A and AP. And book is present only in nominal. Book is present only in nominal. So we'll be writing nominal here. So once we fill the diagonal, after filling the diagonal, then again we'll be starting from the downwards. So combining these two, nominal plus AP. Now I'll check the rule. That will be combining nominal and AP. So combining nominal and AP, is there any rule? No, we don't have any rule. Combining A and nominal. Now I'll check. Combining A and nominal, there's no rule. I have rule for AP and nominal. For AP and nominal, I have a rule. So I can say combining these two, AP and nominal, combining these two, AP and nominal, I can form a nominal. So I'll fill nominal here. Okay. Again, combining nominal and nominal. Is there any rule? Combining nominal and nominal, check. Combining nominal and nominal. Is there any rule? Combining nominal and nominal, there's no rule. Okay. So then we'll try for this one. Then we'll try for these two. For these two, check there's a rule. Like again, we are having AP and nominal as the nominal. So AP and nominal the same here. AP and nominal, there's a rule. Then combining AP and nominal again. This is combination of AP and nominal. That's a nominal here. Then combining AP and the determiner. If you see combining AP and the determiner. Do we have any rule that is combining AP and determiner? We don't have a rule. We have a rule for determiner and nominal. If you see, there is a rule for determiner and nominal. We have NP. For combining determiner and nominal, we have NP. Then nominal and NP. NP and nominal. Again, NP and nominal. Is there any rule? No, we don't have rule for combining NP and nominal. So, here is the steps written how your table is being filled. So, because there's no matching here, so these columns are these cells are left blank, and you can see this is T33 and T34 is being combined to get the nominal. So you can see this cell uh, T24. T24. How T24 is filled? This T224 is being filled by nominal as AP and the nominal. So likewise, all the columns which are filled is written here. So you can see the 1 5 is combination of NP, determiner and the nominal. This is determiner and the nominal. Um, if you see this 3 4, this 3 4, the column number 3 4, you check the column number 3 4. The 3 4 is being filled by 3 3 and 3 4. It's combining AP and the nominal. This is combining AP, sorry, this is combining AP and the nominal. Using these two, this will be filled. So likewise, I'll fill my table using the dynamic programming. And once we make the table, we need not to recalculate again and again. I can make directly my past tree. So here is the past tree corresponding to the sentence given to me, that is a very heavy orange book. So that's all about the context-free grammar. Again, if you like my video, please hit the like button. Thank you very much. That's all about the context-free.